Chapter 1, Section 4, Physics Talk, Changing Speed, Acceleration. When things change speed, it is usually noticeable. The motion of a falling object is a common example of something changing speed. Galileo Galilei, an Italian scientist, was the first person to apply mathematics to the study of the change in the speed of a falling object. To describe the change quantitatively, he needed to make measurements. In the Investigate, you used a motion detector to make measurements of acceleration. Since Galileo lived in the 1600s, he did not even have access to clocks and had to devise original ways to measure time with accuracy and precision. One technique he used involved a water clock. In a water clock, water flows through a funnel into a bowl. The more time that elapses, the more water is collected. To help him explore falling objects, he first investigated balls rolling down an incline. He thought that a ball rolling down an incline was like watching a falling object in slow motion. Through his experimentation with balls rolling down inclines, Galileo found that if he looked at the change in speed with respect to the change in time, the value remained the same as the ball descended the ramp. He then defined this as acceleration. The definition of acceleration as change in velocity with respect to time is still in use today. In this section, you observed, just as Galileo did with rolling balls, that a cart traveling down an inclined plane has a constant acceleration. The velocity of the cart changes at a regular rate and is represented by a straight line on the velocity versus time graph. Acceleration is a vector quantity. Acceleration means how fast the velocity changes. You will recall that the word velocity means how fast an object is going, speed, and in what direction. Velocity, therefore, is a vector quantity. A vector quantity is a quantity that has both magnitude, size, and direction. A bus and an automobile can each accelerate by changing speed from 0 to 60 miles per hour and from 60 to 0 miles per hour when braking, and both can change velocity by driving around curves. But the automobile can produce these velocity changes in much less time. The automobile can exhibit greater acceleration than the bus. The distinction between speed and velocity becomes important when changes in direction can occur. For example, when driving on curves, you can have changes in the direction and thus a change in velocity, even while maintaining a steady speed. For example, a person driving around a curve at a steady speed of 15 meters per second is accelerating. There is no change in speed, but there is a change in direction. So the ways to change your automobile's velocity are to speed up, increasing the speed or magnitude of velocity, to slow down, decreasing the speed or magnitude of velocity, or turn, which is changing the direction of velocity. So again, 3 ways to change an automobile's velocity: speed up, slow down, turn. And of course, you can change the speed and direction simultaneously, as when you drive on mountain roads with curves. All of these motions involve accelerations because the velocity changes as time elapses. In this section, acceleration for an automobile moving along a straight line is discussed. You will investigate changing directions later in this chapter. For now, consider motion a straight line. In one part of the Investigate, you observed a cart going up a ramp. In this case, the final velocity at the top of the incline was less than the initial velocity. This is a negative acceleration. You may have heard the word deceleration used to describe something that is slowing down. However, in physics, that term is not used. The vocabulary used to describe a change in velocity with respect to time is positive acceleration for speeding up and negative acceleration for slowing down. The precision of these terms avoids confusion that may arise when the common word deceleration is used. You will investigate negative acceleration further in section 5. For motion in a straight line, positive acceleration means that the velocity of the object is increasing over time. Negative acceleration means that the velocity of the object is decreasing over time. If the object is moving in a straight line. Vector and scalar quantities. A quantity that involves both direction and size, magnitude, is called a vector quantity. A quantity that has size but not direction is called a scalar quantity. Speed is a scalar quantity. It only indicates the change in position over a period of time in a straight line. Velocity is a vector quantity. It can indicate a change in position over a period of time and the direction. Describing accelerated motion using strobe pictures. Recall that you used 3 different models to describe motion: strobe pictures, graphs, and equations. Each gives the same information but in different forms. You will use the same models to describe acceleration. Because the speed is always changing during constant acceleration, the strobe illustration below shows the automobiles moving greater distances during each second of travel. So they're saying that in the same amount of time, this car traveled this far, and then, I'm sorry, not in the same amount of time, but it's just showing acceleration. All right. Describing acceleration using an equation. In the investigate, you used an equation to describe acceleration. You calculated acceleration by finding the change in velocity with respect to time. Oh wait, yeah, they are saying in the same amount of time this car traveled this distance, and in the same amount of time this car traveled this distance. So this car was traveling faster than this car. Oh, that's what they're saying. All right. Describing acceleration using an equation. In this investigate, you used an equation to describe acceleration. You calculated acceleration by finding the change in velocity with respect to time. All right, so this is the serious part here. Okay. Acceleration equals change in velocity over change in time. This relationship can be written as an equation using symbols. So they're saying acceleration equals change in velocity over change in time, where A is acceleration, change in velocity is a change in velocity, and that's your change in time. Units for measuring acceleration. To calculate acceleration, you divide the change in velocity by the change in time. The units for acceleration are then, by definition, velocity divided by time. Recall from the previous section, the units for velocity can be meters per second or kilometers per hour. Assume that the time interval is measured in seconds. The units for acceleration would then be meters per second divided by seconds, or kilometers per hour divided by seconds. So they're saying velocity divided by seconds or velocity divided by seconds, but they're in different. One is metric system, the other one is the standard. The change in, miles per second divided by second, or kilometers per hour divided by second. Okay. The change in velocity is given in meters per second. The change in velocity is given in meters per second every second, or kilometers per hour every second. There we go. When writing the units for acceleration, the final units are often simplified. For example, the following all mean the same thing. The simplified units are read as meters per second squared. All right. Okay, meters per second divided by seconds, meters per second divided by second, or not or. So this equals this. Okay. In the investigate, you calculated acceleration in feet per second every second, or feet per second squared. Using the equation for acceleration to find other quantities. The defining equation for acceleration shows the relationship between acceleration, velocity, and time. If you know two of these, you can find the third. Okay, so this is the important part. All right, so the three units you have: acceleration, change in velocity, change in time. Using algebra, it follows that change in velocity equals acceleration times time. Time equals change in velocity over acceleration. Using symbols, these equations can be written as, here we go, acceleration equals change in velocity over change in time. Change in velocity equals acceleration times change in time. Change in time equals change in velocity divided by acceleration. Like I said, if you need clarification, or if you even need one-to-one support while you're working on this, just contact Miss McEntee, or contact Mr. Harrow, or contact Miss Scoville. But I would say mainly contact Miss McEntee or myself, and I can give you one-to-one support. She can give you one-to-one support, although she teaches a lot more classes than I do. So if you really want the one-to-one, just reach out to me, Mr. Harrow, and I can kind of walk you through this stuff. Okay. We want everybody to pass, and I want to support you fully in that. All right. Let me scroll down a little bit. As you did with the equations for speed in the previous section, you may find it helpful to use a circle like the following. Now, I think you can see my mouse right now. So it's like, okay, so if you're trying to find acceleration, I'm going to cover up acceleration because that's what I'm trying to find. Then look, I just do change in velocity by change in divided by change in time. If I want to find velocity, I'm going to cover that up. It would be acceleration times change in time. If I want to find change in time, you just cover up whatever you want to find. So if I want to find change in time, I'm going to cover it up, and then it would be change in velocity divided by acceleration. The only time you multiply is when you cover this up, because this is the multiplication here across, and then this is dividing. But again, just let us know. All right. By covering up the variable you wish to find, you can see the equation to find change in velocity. Cover up velocity, you see acceleration times change in time. To find acceleration, cover up the A, and then you see, let me go over this again because this is better than what I said. All right, by covering up the variable you wish to find, you can see the equation. Here we go. To find change in velocity, cover up the velocity. Then you see that it's acceleration times change in time. To find acceleration, cover up the acceleration, and you see change in velocity divided by change in time. To find time, cover up the change in time, and you see change in velocity divided by acceleration is change in time. All right, there's only one definition of acceleration. Algebra allows you to write it in different forms. Okay, so it's, all right. Sample problem. At the start of a race, a toy car increases speed from 0 meters per second to 5 meters per second as the clock runs from 0 seconds to 2 seconds. Find the acceleration of the toy car. Strategy. Use the definition of acceleration as the change in velocity over a change in time. So what are they asking you to find? They're asking you to find the acceleration. So that means we're going to cover up acceleration, and then it's change in velocity over change in time. Now, did they give us a change in velocity and did they give us a change in time? Well, yeah, they did. So 5 meters per second is your velocity. 2 seconds is your time. So according to this, it would be 5 divided by 2. But let's see if that's what they're saying. Yeah. Okay, and again, we're here to support you on this. All right. So for that solution, they did 5 divided by 2, and that was 2.5 meters per second. So that's your acceleration. The acceleration is 2.5 meters per second every second and can be written and stated in 3 ways. You could say 2.5 meters per second every second. You could say 2.5 meters per second, or you could say 2.5 meters per second squared. Describing acceleration using graphs. A third way to represent acceleration is with graphs. If the distance is represented on the y-axis and time is represented on the x-axis, then the graph showing constant acceleration is a curve. The slope of the tangent line of the curve at any point gives the instantaneous speed at that point. One such tangent is shown on the graph below. If you imagine tangents at different points, you can see that the slopes of the tangents increases as time increases. Thus, the speed is increasing during this time. An increasing speed during a time interval is an acceleration. If the velocity is represented on the y-axis and the time is represented on the x-axis, then the slope of the graph will be equal to the change in the velocity with respect to time. The acceleration is equal to the value of the slope of the velocity time graph. Notice that the slope has the same value at all points. You can conclude that since the slope of the VT graph is constant, the acceleration is constant. Describing types of motion using graphs. You can determine the general motion of an automobile by reviewing the distance versus time graph, the corresponding velocity versus time graph, and the corresponding acceleration versus time graph. Each column in the table on the following page provides a way to describe the motion of an automobile. Note, when interpreting graphs, you must always check to see if the y-axis represents distance, velocity, or acceleration. A horizontal line on a graph has very different meanings if the graph is a distance time graph, velocity time graph, or acceleration time graph. Okay. Use the comparing motion graphs table on the next page. Let me scroll down a little bit. Use the comparing motion graphs table on the next page to determine the general motion of an automobile. All of the 3 graphs in a column represent the same motion of the same car. One column gives the information in terms of changes in distance, another represents velocity, and the third acceleration over time. Okay, so distance time graph, velocity time graph, acceleration time graph. Let's dig into this a little bit. Let me see if I can zoom out. We can dig into it a little bit. So I just zoomed out so we can see these. So this is an automobile at rest. And look at that. There's kind of a set for the distance time graph. The distance does not change for an automobile at rest. For the velocity time graph for an automobile at rest, the velocity is always 0 because the position does not change. For acceleration graph for an automobile at rest, the acceleration is always 0 because the velocity did not change. Here's an automobile with constant velocity, okay, meaning that the automobile is set at a cruise control. Distance, position changes at a constant rate. So automobile with constant velocity. Change in distance first time is constant, and therefore the velocity is constant. Automobile with constant velocity. There is a constant velocity with no change in velocity. There is a zero acceleration. Automobile with a constant acceleration. So this is when you're stepping on that accelerator. Okay. Speed is increasing, and it can be seen by the increasing slope of the distance versus time graph. Velocity is changing at a constant rate. The automobile is moving at a constant acceleration. Wait. I'm sorry. For this graph, the speed is increasing as it can be seen by the increasing slope of the distance versus time graph. And then for this, the velocity is changing at a constant rate. The automobile is moving at a constant acceleration. So this was for automobile with constant acceleration. Okay.